So this brings us to our last panel for this event. So the panel is experimental perspective on deep learning, and the subject will be what's missing in today's experimental analysis of deep learning. So I have the privilege of inviting Jitendra Malik, Peter Bartlett, Antonio Torralba, and Isabelle Guyon to the stage, and moderating the panel we will have Jonathon Phillips. Thank you for agreeing to speak.
Welcome to the last panel. The panel is on experimental methods. Just a few words about how we'll run the panel. The moderator in each of the panelists will speak for up to 4 to 5 minutes, and after that's done, we'll take questions from the audience on the topic. I will start myself speaking, and I think we'll just go down in order on the panel. Since I gave a talk right after lunch, I only have a few reflections I would like to make. So, as it was said the first day, one of the organizing principles that started organizing was Ali Rahimi's comment on the alchemy of deep learning. And I've been noting or thinking that a similar comment was made in the 1990s about computer vision. There was a set of opinion articles, this is before YouTube, on the state of computer vision, and one thing that actually jumped out was comparing computer vision to a child learning to ride a bike. And the statement that stands out in my mind was, "Look, Ma, no hands." So the idea is at this point people would show performance on a couple of images in the paper, maybe their own favorite data set, and look, I've solved it. And this debate that came on went back and forth for a couple of years. But what ended up happening was measurement of empirical evaluations on standard benchmarks. This has now become accepted in the community. There are even some here who maybe say it's the tyranny of these benchmarks. But one thing that we've noticed about here is that the deep learning has been around since the work of, we'll go back to the Cognitron, but also particularly Yang Kun's work starting in the late 90s. And it became accepted in the community once AlexNet's performance was demonstrated on the ImageNet. So it may be a ternary, but it also at the same time allowed when the community saw that here was a breakthrough, we had to pay attention, and it led to the provenance of deep learning, those techniques that we discuss here. So one thing that came out of the previous debate was, I was thinking about this, that Rodney Burks made a statement that the next breakthrough, the research is being going on here currently in the community, we just don't know it. So the question I have from an empirical point of view, assuming that's how it makes a breakthrough, is do we have the data and experimental procedures out there today that if there's a breakthrough and when it appears, will we notice it? Or will we be waiting an extra 5 years or some time period to the data and experimental procedures there to convince the community that this is where we now need to go? And I think at that point, this would be my reflections and comments, and we can further questions or follow up at the question sessions at the end. Jitendra?
Me first? Okay. So I want to start by echoing what Jonathon said. I mean, the state of affairs in, say, computer vision, I'll speak primarily about that, but it's also true in other areas of AI. In the 90s was very bad. It was that everybody had their paper with their own variation of a technique. Their code was kept sort of separate. Everyone, nobody could replicate other people's experiments, and everyone showed results on their 5 chosen images where it worked. So it was like test and training set were conflated. So that situation needed to be changed, and we started to have this movement, and Jonathon's work on Ferret was important. At Berkeley, we developed this Berkeley segmentation data set, which was very influential, both as a way of showing that even a fuzzy task like segmentation could be quantified. We could have many humans mark the boundaries and compare the results of algorithms on that, etc., etc. I think that was one trend which was a good trend at the time. A second trend for which various people can be given credit, but I would cite, say, David Lowe as one example of people putting their code online. That didn't used to happen so much in the 80s and 90s, but in the 2000s, it became the tradition. People like David Lowe did it, people like Antonio Torralba did it. It sort of became the norm. So nowadays, it is the norm that everybody posts their code online at the same time that their paper comes out. And this is a good thing. Okay, so these were two good things. This, in fact, I think facilitated the deep learning revolution because, of course, the accumulation of data did, but the acceptability, because it got us out of ideological debates and made the challenge empirical. So I have to relate my story here, which is I got a phone call from Jeff Hinton somewhere around 2011, and it was just out of the blue. I happened to be in my office, and he called me up, and his first question was, Jitendra, why don't you like deep learning? And it was like no hi, hello, it was why. And I said, okay, since you've asked this directly, he said, because you haven't proved your point. He said, but we have all these results on MNIST and CFAR and so on. I said, well, MNIST, there are 6 different techniques which all give under 1% error rate, doesn't prove a point. And CFAR, it's good, but we don't take it seriously in computer vision. So he said, what would convince you? So I said, Pascal. Pascal was the dominant paradigm at the time. So he said, okay. Then he called me back the next day and he said, Pascal doesn't have enough data. What do you think about ImageNet? So I said, yeah, I think it is easier in one way, but harder in another way. That sounds like a deal. So he said, okay, I'm going to put some students to work on this and I'll call you back if we get good results. Okay. And as you say, as one says, the rest is history. So because so it was great. I mean, people like me who were skeptics, they were convinced by empirical results. Okay. And that's how it should be. However, I feel now there is too much of a good thing. And I personally am actually getting disillusioned of this. And sometimes at lunch, I was sitting with Rod Brooks and I'm feeling guilty now about having pushed this empiricist paradigm, this what Dave calls the common task framework. It has got us, we are raising this generation of students who basically want to fight the battle of the next 0.5% on task X. And the innovations of the next round may come in settings which don't quite conform to our existing models. And so they are going to start out perhaps not being so good. And I think we need to be open to that, and yet it is very difficult. We found the enemy and it is us, in a sense that our reviewing process is such that most of the reviewing is done by inexperienced grad students, and instead of trying to judge ideas, they go by little numbers being slightly better. And our problems, I mean, the phenomena we are dealing with are quite complex, and we should always be open to redefining the problems, right? There is a line, I think from Tukey, which is that it is better to have an approximate solution to the right problem than the right solution to the wrong problem. And in the old days, in the bad old days, we used to go around exploring the problem space much more vigorously, and maybe too vigorously, and we didn't do enough of building on things that work. Right now, I think we've gone way too much in the other direction. So I'm actually now regretful of what I myself did.
Should I go?
Yeah.
Okay, so I agree that the enemy is us, and I think that there have been many battles, so this is not the last one. When I think datasets are a very important part of the experimental side of deep learning, and as we have seen, when people started doing research, at the beginning, the n=1 problem was the only thing that people could actually do. That was the only image that you could upload into memory. And then datasets start to evolve as soon as you had enough memory to actually store them somewhere. And there was a time in which the datasets were not really benchmarks, were datasets that were paper-driven. So you had an algorithm and you just had a dataset that will make your algorithm shine. So you will never build a dataset where your algorithm wouldn't score at least 90% performance. And you can, there is a long list of datasets that had that particular flavor. And the battle here was that first it was very hard to get a paper out or motivate the students to work on a problem where the performance was going to be like 10%. And the second thing was even just to get accepted a paper where the goal was to put forward a new dataset was extremely difficult. And the community was not accepting that as valuable research. So at some point that changed, and that was a battle. And the community started accepting that datasets were a contribution on their own and started accepting as a valid contribution a new benchmark where the benchmark drives the paper. And the performances are horrible, and you have just some baseline, and you show, okay, this is a hard problem, and you build a data set that asks a new question. And what I think is happening is that now we are going to fight new battles. So we've performed really well in building certain data sets that answer certain questions. There are some other areas of the field that are really behind in this construction of data sets. And this is why all the focus of the energy of our students goes into just very narrow classification problems most of the time. For instance, we don't have a data set that will allow us to evaluate like embodied AI, just as we have the ImageNet for classification. So we need these data sets also to motivate the students to work on these areas and to measure progress, because at the end, these benchmarks, what they allow you to do is to convince other people that your method is actually good, because you don't really have a theory to prove it. So the numbers are, at the end, the only convincing thing most of the time. And then there are a number of other issues that happen with datasets that we don't really understand. There are biases, there are ethical considerations, and all of these have enormous implications. And this is a new thing that is emerging now that the models start to kind of work on really difficult datasets. These problems start appearing, and there weren't problems in the past. And I think that finally another thing that is happening is that something that is happening now with experimental science is gotten sometimes too experimental, and it's not just that it's missing theory of the learning. Sometimes the students are actually missing theory of the field in which they are actually applying these techniques. And people, sometimes they just think of solving a particular visual task, and they don't really think too much about what makes sense, which performance makes sense to have, which errors make sense and don't make sense. And it's very hard for them to evolve. I mean, if something works, then it's great. The problem is when it's not working. This debugging process is very difficult. And we don't have nice visualization tools, and sometimes just the students are really good at knowing how to hack PyTorch or TensorFlow and put different pieces together, but they know very little about traditional optical flow estimation or geometry or things like that allow them actually to make sense of the results. That's it.
Okay. Well, so I'm putting now another hat. I was previously just presenting some research of my grad students, but what you may not know is that I'm also a veteran challenge organizer. I'm running a nonprofit to organize challenges in machine learning. Since 2003, we've been organizing challenges for NeurIPS, actually, and since 3 years ago, we have started a challenge program at NeurIPS. And of course, it's not the first challenge program at a conference. I would say that many conferences have had challenge programs. One of the oldest one has been the KDD Cup, and there's been challenge programs in many conferences, including computer vision conferences. IGDAR has had one for a long time. And it's now becoming a little bit the norm that every conference has its own challenge program. And that's tremendously important because benchmarking and conducting evaluations that are free of inventor-evaluator bias does not only consist in putting out some data set that people can download and happily overfit on, but it's also about designing tasks and having good metrics and having evaluations in which people don't have the opportunity of overfitting on the data. And typically, what you want to do is to ask people, in fact, to submit their code and having a blind evaluation, which we are doing more and more. But now, of course, there's some downside of that. Is that the downside is that you might be a reductionist. You might be driving the entire community to only solve tasks that are defined in challenges. And while we solve the inventory evaluator bias, there may be some other kind of bias which is cropping up, which is the bias of the organizers. So in a way, you know, you've already been mentioning that even when you put out a data set, you put out the data set that makes your algorithm shine. And when you organize a challenge, well, in a way, you know, you're biased in one way or another. So how to overcome that? I think one way is to put out open calls for challenges, and that's what we've been doing, you know, in conferences like NeurIPS. There are open calls for challenges in which the challenges themselves are reviewed. But they are peer-reviewed, so the protocol of the challenge, the quality with which the data is collected, everything is reviewed, you know, with criteria that are well-defined. It's not bulletproof, but it's already a lot better than just putting out a piece of data and telling people, okay, that's it, you know, like a piece of meat. And what we've seen is that we've seen an improvement in the protocol of challenges, people becoming aware of subtle kinds of biases, and also not so subtle ones that we've been victim of for a long time already. For example, data leakage is something that's plaguing a lot of the data sets. In statistics, people call that confounding, or sample bias, and other various kinds of bias that have to do with calibration of data. If you have, for example, multiple annotators, they will be annotating bulks of part of the data, and they might not be calibrated with one another. So, well, having said that, I also wanted to give you an anecdote related to Jitendra's story. I forgot when it was. I think it was in 2011 or so. There was a DARPA program for evaluating deep learning, and I was part of the evaluation team. And DARPA told us, well, you know, there's all these weird deep learning that claim, you know, that unsupervised learning can do wonders, and you ought to organize a challenge that tests whether it's possible to learn with unsupervised learning. And we want to do something that has to do with video. And I was like saying, oh my God, you know, I just have to test unsupervised learning, we have to have videos, it's just going to be such a difficult thing to do. So I ended up actually organizing two challenges, one on unsupervised learning, that gave beautiful results, showing that actually you can do most of the work with unsupervised learning. And these results have been forgotten. Interestingly enough, you know, all of deep learning started reviving because of the promise that Jeff Hinton made that thanks to unsupervised learning, you would be able to train these deep nets. All of that work has been forgotten all of a sudden. I don't know why. And it actually, unsupervised learning works really well. So I would like to remind that. That challenge on unsupervised and transfer learning had two phases, one in which kernel methods won against neural networks, and in the second phase it was the opposite, but this was basically a tie. And they showed that you can basically create in an unsupervised way a very good representation, and afterwards with a simple linear neural network trained with Hebb's rule, so it's basically, you know, making independence assumption, you can do as well as it gets. And what we did is that we asked people to submit representations of data, and the organizers ran the supervised learning part to test the representation. So it's interesting that these results have been forgotten. And the second anecdote is that the second challenge we organized was with video data. It was on one-shot learning. So we were too early for the time. This task was really hard to do video data with one-shot learning. And in that competition, even though it had been designed to make deep learning shine, because I was thinking, you know, all of the setting of Jan LeCun's work and making it, you know, that those were people playing gesture in front of a fixed camera, and it was really possible to solve with deep learning. No deep learning method entered the challenge, none of them. And that was simultaneously that AlexNet arose, you know, and showed the power of deep learning on ImageNet. So this was a lesson to me. We were, you know, too early with a too hard task. In fact, Jitendra had told me at the time, you know, why are you working on this too complex video task? You know, look at what they are doing with ImageNet. That's the way you should benchmark things. You should download things from the internet, have real images, have them annotated with AMT. So he was all right with that. But the interesting thing is that the year after, we had a second round of this video kind of a challenge with gesture recognition. And that time, it was 100% of the top-ranking participants that were using deep learning. So it was like a real step function. So this was, you know, my anecdote. Peter.
All right, so I'm the theoretician that got invited to the experimentalist party. So I took the title of the panel, What's Missing in Today's Experimental Analysis of Deep Learning, as an invitation to explore my wish list for what I'd like to get out of experimental research in deep learning. And, you know, it's kind of simple. It's a little different from the perspective of others. I really want to be able to rely on the conclusions that the experimentalists come to. And that sounds like, you know, I'm not talking about intellectual honesty, I'm talking about the direction, you know, rather than focusing on benchmarks, on engineering systems that solve a problem better and better. You know, I'd like to be able to get insight into what's behind the successes, you know, elucidating those aspects of a methodology that are really crucial for performance. And, you know, in preparing for this, I put together a list of the approaches, tricks, tweaks, all sorts of things that we've heard at various stages are crucial for good performance, and then at other times we hear, well, they're not so important. So unsupervised pre-training was one of these, dropout regularization, ReLU nonlinearities even, batch normalization, various other things, completely connected layers, mini-batch stochastic gradient. A lot of these things, I think it would be really valuable to understand the science of it, you know, and careful experiment design, teasing apart, you know, what's important from what's spurious is difficult, but I think it's really important. Very different goal.
Can I answer Peter too?
Actually, would like to take one or two questions from the audience in our time. Are there any questions from the audience?
A little remark at the end of Jonathan Phillips's talk that I noticed was the one about designing a challenge that's good for a decade. And to some extent, I think actually NIST has had a fairly good track record of that in the sort of end part of the 20th century. And it seems like in the current decade, what's been happening is much more that challenges are only good for 2 or 3 years. Now, that could just be because successors are building so much faster with deep learning that everything gets solved in 3 years. But I wonder if there's sort of more to learn about having long-term challenge successors, which maybe you know, but the grad students who build a lot of the data sets now don't.
So I'll take a quick comment. Actually, when I had the version of the slides this morning, it was 20 years. And I didn't mean that we design a challenge problem that's useful for 10 years. What I meant was I'll be seeing papers that report on it for 10 years when they maybe should retire at 5. But I think part of the thing I've noticed is this too, that I think because of the capabilities of deep learning, and a lot of times these challenge problems, here's the training set and here's the validation, that it's a lot easier to learn the function that will optimize performance given a training set with maximizing the validation set. So I think it's the power of the deep learning. I don't know if people have done a sequestered data set, if this would make the problem longer, that they couldn't they couldn't do a quick hill climbing to solve that problem. It would be a longer time frame. Any other?
I mean, in computer vision, it's more like 5 to 10 years, I would say. I mean, so far, that's the number. But the big problem is really when you release the test set, and because then obviously there's overfitting through the various cycles of people trying to get better and better numbers.
So I think it's very important to run recurrent challenges on the same topic for a number of years to really ramp up performance. It's also important for people to be able to collaborate, because there is this mix between competition and collaboration. We've been trying to do a lot of competition design that we call co-opetition, where we mix collaboration and competition. But we found in the end that the best way is to run recurrent events. And these are checkpoints where everybody publishes and exchanges ideas, exchanges code, and then we go to the next round of challenge. In order to avoid to fall in too quickly in a local minimum, having open call for challenges and having people renew, their protocol, their data, makes it that there is enough, new things going on a particular topic.
Yeah, my comment is not on experimental data, but since we have a theory panelist, I think I could be excused. In the morning, we heard about the challenges, that is the instabilities in the networks and the way neural nets are done. And it seems the system seemed to work, but we have these instabilities, and I was thinking of how to deal with it. And one way is to have a general framework in which these processes can be put together. Because when we say instability, generally we think of changing in time, something growing. And when we think of something growing, it could be a wave or something like that, dynamics. And when we think of dynamics, then we need to have a space in which we represent that dynamics. And that has to come from the data. It would be nice if we have a mathematical theory at this time, but I don't really see it. But from the data, we have the dynamical systems framework in which the data can be put in a systematic way, define an orthonormal set of vectors so that you can study dynamics, do prediction, define these manifolds, do the statistical mechanics. And then we'll be able to follow these dynamics and look at these big events. And big events generally are not just something growing very quickly to some large value. It is an interaction of many things. And what are those things are essentially like eigenfunctions or the typical features of that system. And their interaction leads to big events or extreme events. And I think extreme events in networks or in deep learning has an important place. And extreme events was in fact the theme of a Sackler symposium few years ago, and I think we see that such large events are going to occur, and we need to look at how to deal with those things.
Well, I would like to thank you very much for making these remarks, because actually that was on my list. It's totally true that we need to have designed data sets, that we tend to collect data that have natural distributions, and those are good, but we also need, particularly in cases where there can be extreme problems, extreme cases, we need to have designed data sets. And one step towards that has been the adversarial attack and defense challenges, in which there were teams that were trying to challenge other teams with extreme cases. So we need to do more of those, but I think we need to think very much in depth about the experimental design and how to design proper data sets to corner the learning machines where they should perform well. Also because we, if we have the natural distributions, and of course we like that, you know, from the theory point of view, it's easy to deal with IID data and natural distributions. But when you test and you have very few errors, your error bars are terrible. So we need to enrich, I think, the test sets and perhaps even the training sets with those hard cases in which you get errors.
Yeah, I'd actually suggest that being able to guarantee against instabilities of this kind, you know, that's inherently a theoretical question, right? You would like to be able to prove something about properties of a system. You know, it's not something that an experimental setup is going to give you great assurance about.
Yeah, this is actually where I wanted Peter to go to and give us, you know, what could theoreticians give us as guidelines on how to design data sets that would really corner learning machines into proving that they are reliable?
Well, I don't know about designing data sets. I mean, I think you could draw inspiration as the question was alluding to, draw inspiration from systems theory. You know, we have a beautiful understanding of what happens with linear systems and what sort of properties will lead to instability and what sort of properties will lead to a controlled system staying nice and stable and within the limits. And it's that sort of theory that you know keeps controlled dynamical systems safe in some sense. We have theoretical guarantees about what's going on. I mean, I think that's the sort of direction we should be pursuing for coming up with guarantees. You know.
No, can I ask one more question?
Can we still? Okay. I have 3 subsections, so you can choose if there is no time. The first, I want to go back to the attack-defense type of competitions. So many doing them the way that you can always see who are the best from the defenses, and then people attack them. How do you make them fair in the way that all defenses are standing against everybody and all attacks are standing against everybody? And is there a way to define in ahead of time who is the winner? Like, how is it really evaluated in a fair way? My second sub-question is about the size of the award. So you guys have a lot of experience, and I know that many awards are like 10,000. If you wanted, like, really make a difference, if there was like 200,000, there would be more people, less people, there is no point. Like, what's your thought about the size of the award in case you have agency that allow you to do whatever? And the last, you talked about collaboration, which I think is a very important part from my point of view for challenges. So if you have sub-parts, let's say you had images, video, audio, if you tell in advance to people that you will have a sequence of challenges instead of one, will they already collaborate? Or if they know that there is a next one, they'll still keep everything to themselves, so that if they want the first one, they will be the only one who knows about it when they go to the next? So it's 3, sorry. Whatever. Everybody that can get there.
I couldn't really answer the first question, so the answer will be quick, because I was not designing that particular competition myself, and I can't remember on top of my head what the design was sufficiently to answer whether it was fair or not in terms of evaluating, you know, the adversarial attack and defense. So I'd have to go back and look at this more carefully. Regarding the second question, it's about prize money, right? That's an interesting one, because a few years ago I took all the Kaggle challenges and I plotted a number of participants versus prize, and there's virtually zero correlation. So, and we've also experienced that ourselves in the challenges we organized. We had some that were very, very successful with small prizes and vice versa. Also, in fact, it's sometimes giving big prizes gives you the opposite result than what you would want. It attracts a lot of people that just want to compete for prizes and sometimes try to cheat, or they don't put, good energy into doing good science. Whereas if you have small prizes, you get, the PhD students who really want to put energy into it to publish and solve really the hard problems. So for the third question, I forgot, there was the...
Collaboration, if you have...
all right. Yes, we've tried all sorts of things. And it can get fairly complicated, the kind of incentives you give to people to collaborate while competing. Then it's a multi-objective problem, and people are kind of torn apart between competing and collaborating. Sometimes they naturally collaborate. So it's interesting, you have the people at the top of the leaderboard, usually they don't collaborate, they compete with one another. And you have, of course, a long tail of people, and those are the people who are just there only to learn a little bit about things. And then you have the middle range of people, and those are the people who collaborate with one another to try to climb up the leaderboard and beat the top people. And so often if you have, a forum that allows for exchange, naturally people team up in order to try to climb up the leaderboard. We have fancier ideas, like we wanted to create kind of a little market economy in which people would share modules, and they would start the challenge with a budget of points, and then they could, for points, for virtual cash, license their modules or buy somebody else's module or something like that. But we never really got to implement that. If you want to fund it, we'll be happy to do it.
I see David Donoho being very quietly coming up, thinking what we want to move on. I would like to thank the audience for their great questions, and I'd like to thank the panelists for participating.